Good morning, students. Welcome back. We shall continue the probability, that is axiomatic probability. Already we know very well in the axiomatic probability the definition and three important points related to the axiomatic definition of probability. And one example, in a coin tossing experiment, we can assign the number 1 by 2 each of outcomes, head and tail. Does this assignment satisfy the condition of axiomatic approach? Can you please? Yes, this assignment satisfies the condition of axiomatic probability. In this case, the probability of H is equals to 1 by 4 and probability of H is equals to 3 by 4. Am I right here? And also, we find that both assignments are valid for the probability of head and tail. Now, we continue the another example on axiomatic approach. Students, the assignment satisfies both conditions of axiomatic approach of probability, you know it. Hence, we can say that there are another many ways to assign the probabilities of outcomes of an experiment. Consider another one example. Let the sample space S be denoted by omega 1, omega 2, omega 3, omega 4, omega 5, omega 6. Be a sample space. Find which of the following assignment of probabilities to each outcome are valid here. Yes, you see. First, you can write outcomes omega 1, omega 2, omega 3, omega 4, omega 5, omega 6. Then, hence the total number of sample space be 6. The first one probability is 1 by 6, second 1 by 6, then third 1 by 6, fourth 1 by 6, fifth and sixth is also 1 by 6. Yes. Another one, let us consider as A. The B, 1, 0, 0, 0, 0, 0. Yes. In the solution part, how can you assign the probability of each is valid or not? For the case A, here the probability of first one is equals to 1 by 6. because omega of integer defines here I is equals to 1, 2, 3, 4, 5, 6 implies 0 less than probability of omega I less than equals to 1, less than equals to 1, which is true for all omega I belongs to S. Omega I belongs to S. And sigma probability of omega I is always, means total probability of all these is equals to 1. 1 by 6, first one, 1 by 6, second one, 1 by 6 for the third one, 1 by 6 for fourth one, 1 by 6 for fifth one, 1 by 6 for sixth one. All together is equals to 1. Hence the assignment of the probability is valid, which should be equals to 1. This is our condition already. It is studied under in the definition of axiomatic approach for the related significance notations. This is for the one. Hence it is valid. Secondly, B, the probability of omega I is equals to 1, and second one, probability of omega 1 is equals to 1, probability of omega 2 is equals to 0. Here he has given all except first one altogether are equals to 0. Am I right here? Altogether are equals to 0. Yes? Then therefore first condition, what is the first condition? 0 less than probability of omega I, which is less than equals to 1, is satisfied. First condition is satisfied because it is less than 1 or equals to 1. Also, probability of omega 1, omega 2, omega 3, omega 4, 5 and omega 6 is equals to 1. The second condition is also satisfied here. Hence, whatever the given assignment is valid. Whatever the given assignment is valid. But in another examples, some assignments are not valid because each of the probability of number P of omega I, which is either 0 or less than 1. So sometimes they are greater than 1. The value is not assigned. Yes? But now again we shall continue probability of an event. An event. See, let S be the sample space. A sample space associated with the experiment examining 3 consecutive pens produced by a machine and classified as a good condition of the pens, they are non-defective, and bad condition of the pens, they are defective. Yes, you understand clearly here. Students, right? Once again, let S be a sample space associated with the experiment examining 3 consecutive pens produced by a machine and classified as good condition means non-defective pens. Bad conditions means defective pens. We may get 0, 1, 2 or 3 defective pens as a result of this examination. See, once again, we may get 0, 1, 2 or 3 defective pens as a result of this examination. Am I right here? So, you see, the sample space is defined S is equals to B, 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 G, B, G, B, G, B, 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 G, G, and G, B, G, 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 B, G, G, G. Am I right here? How many sample space we got? 1, 2, 3, 4, 5, 6, 7, 8. Total number is equals to 8 outcomes. Because they selected bad pens and good condition of the pens. Good conditions are denoted by capital G. They are non-defective. Bad condition of the pens are denoted by capital B. They are defective. Let the probabilities assigned to the each outcome as follows. 8 number of the outcomes are there. Each the probability is assigned to each outcome. Here sample points are there. Outcomes are there. The first outcome is B, B, B. Its probability is 1 by 8. Because generally the probability formula P of A is equals to number of favorable events to the total number of the events. There is a ratio. Probability, first one is 1 by 8. Because 3 bad condition of pens we defined here. We find out 3 bad conditions of the pens. Then from total number of the 8 events, 8 outcomes. Hence, how many number of the bad conditions? Altogether 3 are bad conditions belongs only 1. Hence, that's probability is 1 by 8. Similarly, in this event, 2 bad condition pens are there. 1 is good conditions. Hence, the probability is also equals to 1. Let the event A defines here. Let event A implies there is exactly 1 defective pen, and B implies at least 2 defective pen. From the group of 8 outcomes of the sample space, we can assign them in 2 categories. A, there is exactly 1 defective pen, and B, there is at least 2 defective pens. Means, hence we can separate, make it as a group or set. A is equals to B, G, 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 B, G, 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 B. What A defines here? It defines here exactly 1 defective pen. B means defective pen. In this outcome, B, G, G, 2 pens are in good condition, 1 is defective. 2 pens are non-defective, 1 is defective. Here first pen is in good condition, second one is bad condition, third one is in good condition. Here first 2 pens are good conditions, third one is bad condition. That means in each outcome, each event, 2 pens are, at least 2 pens are good condition, bad conditions. Okay. The set B assigns there is exactly one defective pen and there is at least two defective pens. B, B, G. Second outcome, B, G, B. At least two defective pens must be in a outcome, each outcome. G, B, B and B, B, B. Yes, am I right here? The set A and set B are assigned like this. Once again, you recall. Now, we have to find probability of A. A set consists three outcomes. Therefore, probability of A is defined sigma or summation of P of omega I, where omega I belongs to the set A. Therefore, that's equals to probability of first outcome, probability of second outcome, probability of third outcome. But in the set A and B, there are some conditions. At least one defective pen means bad pen, and in the second option, at least two defective pens. So P of B, G, G, that's equals to 1 by 8. P of G, B, G, that's equals to 1 by 8. And P of G, G, B means probability of G, G, B, that's equals to 1 by 8. Hence, totally, by simplifying these fractions, we will get here 8 is the LCM, 1 plus 1 plus 1, that's equals to 3 by 8. Am I right here? Yes. That means probability of A is equals to summation of P of omega I, where omega I belongs to the A and omega I belongs to A, P of GGBG plus P of GBG plus P of GGB means probability of two non-defectives and one defective. Yes, here first one is defective and next two are non-defective. Here first one is non-defective, second one is defective, and third pen one is non-defective. And here first two are non-defective and last one is defective pen. B means bad pens. Yes, G means good pens. But condition of the set A defines here, A means there are exactly one defective pen and rest are non-defective pens. Am I right here? So carefully you understand. Don't make it as a confusion. Yes, hence the probability of A is given by 3 by 8. Similarly, the probability of B. Probability of B is equals to summation of P probability of omega I, where omega I belongs to set B. But what is the condition of B? At least two pens are non-defective and one is defective. Yes. In the set B, at least two pens are defective. Set B is having outcomes of two defective pens, one is non-defective. Here, first pen is defective, second one is non-defective. third one is defective. Okay, not see. Yes, 1 minute. Yes, first in the set B, two defective pens, one is non-defective. In the second outcome, first one is defective, second one is non-defective, and third one is defective. In the third outcome, third event, first one is non-defective, second and third pens are belongs to defective, but last outcome all containing defective pens. Hence the probability of event B assigned here, summation of sigma probability of omega I, where for all omega I belongs to set of B. Therefore, probability of first event for first outcome plus probability of second outcome, probability of third outcome plus probability of fourth outcome, all together are equals to 1 by 8 plus 1 by 8 plus 1 by 8 plus 1 by 8. Hence 8 is the LCM. 1 plus 1 plus 1 plus 1 equals to 4. 4 by 8 is nothing but equals to 1 by 2. Hence the probability of set B gives 1 by 2. Hence the probability of set A gives 3 by 8. This is another example where the two pens are having defective and non-defective conditions. Yes. Then next one is probability of equally likely outcomes. In this probability, what we shall study? Let a sample space of an experiment be S, omega 1, omega 2, omega 3, so on, if all the outcomes are equally likely to occur. Here all the outcomes are equally likely to occur. That is, a chance of occurrence of each sample event must be same. Likely means same. Equally likely. Andre ಎರಡು ಸೇಮ್ ಇರಬೇಕು. Here means that is a chance of occurrence of each sample event must be same. Am I right here? That means how can you understood the equally likely events? If probability of omega I, that's equals to P for small p for all omega I belongs to S, but condition where 0 less than equals to p less than equals to 1. Therefore, since summation of probability of omega I is equals to 1, that is p plus p plus p plus so on p n times, which should be equals to 1 here. That means number of probabilities of the events is equals to 1. Hence, P is equals to 1 by n by take n this side, divide by this. Then let S be the sample space and E be an event and E be an event such that n of S is equals to n, because the equally likely events. N of E equals to small m, because equally likely outcomes. Yes, if each outcome is equally likely, then it follows that means here the formula is assigned for the equally likely outcomes of each event. Therefore, the probability of equally likely outcomes are assigned by the formula that's equals to m by n. Small m here defines number of elementary events, number of outcomes are favorable to the E divided by total number of the possible outcomes. N of S is always denoted by small n here. N of E is always denoted by small m here. So m by n, which gives number of outcomes of favorable to event E divided by total possible outcomes. This is the formula to define equally likely outcomes of the probability. Yes? Is it clear? You understand? If you are having any difficulty, you ask me. Yes? Okay. Bye. Goodbye.